Welcome to The Explainer. Today we're diving into one of the absolute cornerstones of electronics, Ohm's law. Now, I know it sounds a little intimidating, but trust me, by the end of this, you'll see it's actually super intuitive.
So let's start with a really simple question you've probably even seen for yourself. It all boils down to this really neat relationship between three key ideas in electricity.
All right, first up, a simple, bright idea. We're going to build our intuition here with a little thought experiment. Okay, picture this. You take a tiny little battery, hook it up to a bulb, and you get a dim little glow. Now you swap that out for a bigger, beefier battery, and the bulb gets way brighter. But then, if you try to plug that same little bulb straight into a wall socket, pop! It's gone in a flash. There's a really clear pattern here, right? More power means more glow, until it's just too much.
So it really feels like there's some kind of electrical push happening. The stronger that push, the brighter the light. And you know what? That's not a bad way to think about it. Turns out, science has a specific name for that push.
Let's move on and put some official physics terms to what we've just seen. Don't worry, it's actually simpler than it sounds.
That push we were just talking about, that's what we call voltage. And the best way to think about it is like water pressure. A small battery has really low pressure, while a wall socket has incredibly high pressure. We're talking 1.5 volts versus 220 volts. That's why it's also called potential difference. There's a huge difference in electrical pressure.
And what happens when you have water pressure? You get a flow of water, right? Well, it's the exact same idea here. Voltage creates a flow of electricity, and we call that flow current. It's the current that's actually doing the work, flowing through the bulb and making it heat up and glow. So more voltage pressure gives you more current flow. Simple.
So what we have here is a really simple relationship. Voltage and current are a team. When voltage goes up, current goes up. When voltage goes down, current goes down. You've actually seen this. You know when the lights in your house kind of dim for a second? That's a temporary drop in voltage, which means less current is flowing to the bulbs.
Okay, but this relationship isn't quite a perfect formula just yet. To turn this into a real law that we can use, we are missing one absolutely crucial piece of the puzzle. Right now, we know voltage and current are linked, but in the world of math, to change that proportional to symbol into a hard and fast equal sign, you need to introduce some kind of constant that defines exactly how they're linked for any specific situation.
And in electricity, that missing piece, that constant, is called resistance. And it is exactly what it sounds like. It's how much something fights back against the flow of current. You can pretty much think of it as electrical friction.
Let's go back to our water analogy. A copper wire has super low resistance. It's like a big, wide, smooth pipe. Water, or current, just flows right through it, no problem. An iron wire, on the other hand, has higher resistance. It's like a narrow, rusty pipe that chokes the flow. So even with the same amount of pressure or voltage, you're going to get a lot less flow or current through that iron wire.
And with that final piece in place, we get the whole shebang, the famous formula that ties it all together. Voltage equals current multiplied by resistance. This is Ohm's law. And with this one simple equation, we can predict exactly what's going to happen in a basic circuit.
So we have this amazing, powerful law. But, and this is a big but, it doesn't just work for everything all the time. There's some really important fine print we have to talk about.
This is the part that a lot of people miss. For Ohm's law to actually hold true, two things have to be constant. First, the temperature of the wire can't change. And second, the physical shape of the wire, its length, its thickness, can't change. If either of those things changes, the resistance itself changes, and our neat little V equals IR formula just falls apart. This is absolutely critical to remember. Okay, now let's take a look at how this all looks on a graph, because this is where things get really practical. And it's also where you can find a really common trick. So, when we plot Ohm's law, the standard way to do it is to put voltage on the vertical y-axis and current along the horizontal x-axis. For any material that follows the law, what you get is a perfect straight line starting from the bottom corner and going up. But here's the really cool part. The steepness of that line, the slope, isn't just random. Remember from math class, slope is rise over run? Well, here the rise is voltage and the run is current. So the slope is V divided by I. And if you just rearrange Ohm's law, you'll see that V divided by I is exactly equal to resistance. So a steeper line means higher resistance. Pretty neat, huh?
But here's the trap. This is what you might see on an exam. What happens if they flip the axes on you?
What if current is now on the vertical axis and voltage is on the horizontal?
At first glance, it looks almost identical. It's still a straight line going through the origin. But don't be fooled. The meaning of that line has been completely turned on its head.
And this is how they get you. The slope is still rise over run, but now the rise is current and the run is voltage. So the slope is I divided by V, and according to our formula, that's not equal to R, it's equal to 1 times divided by R. This means a steeper line on this graph actually means less resistance.
So the huge takeaway here, the one thing you absolutely have to remember is simple. Before you even think about interpreting one of these graphs, always check which quantity is on which axis. It'll save you from a world of hurt.
So we've pretty much mastered the rule for materials that play fair, the ones we call ohmic. But that leaves us with one last really interesting question to chew on. What's going on with all the other stuff out there, all the materials that don't follow this nice, neat straight line rule? Well, that's a whole other story for another explainer.